The argument for why ElGamal encryption is secure is quite similar to the argument we made for Diffie-Hellman, which makes sense since ElGamal encryption is based on the Diffie-Hellman key exchange. So remember that the Diffie-Hellman key exchange was secure because of the Diffie-Hellman problem, which itself was based on the discrete log problem. And the Diffie-Hellman problem goes like this. If someone gives you g to the a mod p and g to the b mod p, it is hard for you to recover the shared secret g to the a b mod p. That's what the assumption says, and we assume that to be true because the discrete log problem is hard, and no one has found a good way to solve this problem besides discrete log. Now, ElGamal sends these values over the insecure channel. So if you're thinking about Eve, these are the values that Eve can see. Eve can see Bob's public key because that's published to everyone, and Eve can also see the ciphertext that Alice sends across the channel. And remember that the ciphertext is actually two values. It's big R to complete the Diffie-Hellman key exchange, and then it's the message encrypted with the shared key. These symbols are kind of confusing, so we can actually write out what they represent. Big B is g to the little b mod p. Big R is g to the little r mod p. And the message is encrypted with g to the br mod p, the shared secret. Now, if we look at this, g to the r mod p and g to the b mod p, well, that's exactly the two values given in the Diffie-Hellman problem. And the Diffie-Hellman problem says, even if I tell you these two values, g to the b mod p and g to the r mod p, it is hard for Eve to derive g to the br mod p. And because she can't derive g to the br mod p, she is unable to reverse the encryption and obtain the original message m. If Eve wanted to get the original message m, she would have had to multiply this value by g to the negative br mod p, but she doesn't know that value because she's only given g to the b and g to the r. She is not able to derive the shared secret, so she cannot cancel out the g to the br to get the original message back. So this is not a proof, but it's a rough argument for why Eve, the eavesdropper, is not able to recover the original message in ElGamal encryption. ElGamal encryption provides confidentiality, but it does not provide integrity. One attack that attackers can do on ElGamal encryption is something called malleability. In this attack, Mallory, a man-in-the-middle attacker who can tamper with messages, is going to change the message and cause Bob to decrypt something that is predictably different. Now that's kind of a subtle point, so let's go through an example. Let's say that Mallory sees some ciphertext and she doesn't know what the ciphertext says. But based on the malleability attack, Mallory is able to modify this ciphertext in some predictable way so that when Bob decrypts the message that he decrypts has also changed in some predictable way. For example, if the malleability attack is used to double the value of the message, then what this means is that if Alice sent the message 25 and Mallory executes her attack, now when Bob decrypts the message, he ends up seeing 50, a number twice as large. Or if Alice's original message was the number 70, then when Mallory executes her attack and Bob decrypts the message, Bob will see the number 140, which is twice the original value. It doesn't matter what value Alice sent originally, and it doesn't matter that Mallory doesn't know what the ciphertext says. She is able to execute an attack so that no matter what the original number was, Bob is always decrypting a number that is twice its value. That's the malleability attack. It means even if you don't know the ciphertext, you can cause Bob to get a message that is predictably different, for example, twice the original value. All that being said, ElGamal encryption is vulnerable to an attack like this, and as an example, we can show you how Mallory is able to cause Bob to decrypt to a value that is twice the original value. So if we go all the way back to the encryption scheme, let's say that Alice sends the ciphertext, which is two values. It's the big R value, which is part of the Diffie-Hellman exchange, and then it's the message multiplied by the shared secret. Now, if Mallory takes this ciphertext, intercepts it, and she replaces C2 with 2 times C2. So whatever value it is in ciphertext, she takes that value and she doubles it. Well, then what's going to happen when Bob decrypts? When Bob decrypts, this value is now twice its original value. And if you go through all its math, there's an extra factor of 2 here, there's an extra factor of 2 here, there's an extra factor of 2 at the end. So when Bob decrypts the message, he ends up getting 2 times the original intended message. So ElGamal encryption is vulnerable to this malleability attack, where Mallory takes not the first, but just the second part of the ciphertext, multiplies it by 2, and now it looks like the message being sent is not M, but 2M. And when we go through all the decryption steps, we can also see that Bob ends up decrypting a value of 2M. So to make a long story short, ElGamal encryption doesn't offer integrity. Attacks like malleability are possible. And one final word of warning is that ElGamal encryption, as we've presented it, actually is not IND-CPA secure. There are some very subtle points that we haven't really talked about that cause the scheme that we've shown to not be secure. So if you want IND-CPA security with ElGamal encryption, you have to add some additional subtle points that we're not going to talk about. So just remember that the scheme we've shown is not quite IND-CPA secure, but with some modifications, it can be made to be IND-CPA secure. And that's it for ElGamal encryption.